January 1994, Northridge, California. For anyone that remembers that day, the images of devastation are frozen in memory. The earthquake wreaks havoc on infrastructure and buildings. Freeways, businesses, and homes are destroyed or rendered uninhabitable. Yet even though this powerful quake strikes one of the most densely populated regions of North America, less than 100 people perish. While modern engineering did much to minimize loss of life, this devastating event provided an opportunity to improve future design.
The beginnings of this project come out of the 1994 Northridge earthquake. During that earthquake, 9 parking garages collapsed. This occurred at 4 o'clock in the morning, and so only 1 life was lost. It would have been much more devastating 3 hours later during rush hour. Several of those parking structures are precast concrete. The failures in the Northridge earthquake pointed out the susceptibility of the floor systems to come apart.
In engineering terms, structures are comprised of 2 main elements: frames, or the vertical and horizontal members, like columns and beams, and diaphragms, or the floors, roofs, and ceilings. In 1999, a consortium of industry and academia headed by PCI, the Precast Pre-Stressed Concrete Institute, and the National Science Foundation conducted the landmark press test to verify design methodologies for precast frame systems to withstand seismic forces. Now, a similar consortium headed by PCI is addressing methodologies to design floor systems or diaphragms to more effectively contribute to a structure's seismic performance with the Diaphragm Seismic Design Methodology, or DSDM project.
The performance of floor systems during an earthquake is very complex, and it's actually one of the less understood behaviors. Code changes were made over the years, but in 2002, PCI recognized that they needed a new design methodology specifically for their systems. So they issued a request for proposal, RFP.
The project originated with PCI. PCI has acted kind of as the germ cell of the project and coordinator of the project. But to do a project of this magnitude, it's different than most of the other projects we've done, which PCI has pretty much managed itself through our research and development committee. This one, because of its scale, we're over $2 million invested in this, and possibly going up to $2.5 million, required a lot of collaboration and participation. But it's not just for the money. It's also because the knowledge and specialty information that we needed, special equipment, special techniques, analytical tools, can only be gotten by reaching outside our immediate industry and involving people who have an interest and expertise in this area. So as a result, you're seeing a project here that's the culmination of a really wonderful collaboration. Not just money coming together, but people's minds and ideas coming together.
Also helping to bring minds and ideas together were the contributions of the Charles Pankow Foundation.
We exist to advance innovations in building design and construction so that the public will end up with buildings of improved value and quality and efficiency. It's really a practice-serving, research grant-making foundation, and still very young. We're just into our 3rd year of grant-making. It was a real pleasure for the foundation on our very first year of grant-making to learn that PCI and this project was proceeding on a path exactly as we intend our research contributions to do, so that something over $400,000 of the Charles Pankow Foundation grant is helping this DSDM project go forward. Its purposes to deliver final building codified results in innovative precast diaphragm construction are extremely well aligned with the purposes of the foundation.
As with the landmark press test, completing the collaboration are 3 preeminent American universities.
The way that this project was organized, it has a large input from industry. Really, there's three university organizations. There's the University of Arizona, headed up by Robert Fleischman. He's really the team leader for the whole project, and he made this really happen. He brought together University of California at San Diego and Lehigh University. At Lehigh University, there's Richard Sauce and myself, who have been doing a lot of the work on the small details. At San Diego, it's more of looking at the whole system, while at Arizona, it's taking pieces from both of our groups and working them to have a combined study on all of these issues in a computational model.
We realized from our previous work when we started this project that we couldn't focus on just one level of behavior. We couldn't look at the overall structure, we couldn't look at the details, the reinforcing details, or look at the individual floor systems. We had to look at all three. And we broke out the work among the universities that way. UCSD's focus is on the structural system. Lehigh University's focus was on individual reinforcing details, and we're the kind of the glue that holds it together by looking at the floor systems and focusing mostly with computer simulation. So the way we decided to perform this project is have Lehigh do tests of existing reinforcing details that are used in the floors today to examine their performance, see if the performance was good and bad in terms of strength and stiffness and deformation capacity, which we call ductility, and also to characterize them so that we could actually take experimental data from Lehigh and build our computer models of floors. Then we did earthquake simulations of the structures with those models, and at the back end we want to validate our computer models that it's taken a number of years to build by making predictions of a structure like the structure behind me and actually simulating an earthquake with the structure here at UCSD.
One of the things that makes this, this floor diaphragm study unusual and unique is that the structural system we're looking at is very large scale. So we imagine floor diaphragms in plan or looking down from the top of maybe 100 meters in one direction and 60 meters in the other direction at full scale. That's what those buildings really look like. And so to study this and develop better ways of designing them poses a great challenge. Now we can shrink them down in scale, but then the critical details become too small and we don't really model them accurately. So what we're using is a combination here of numerical simulations to really capture the behavior of the large system. Large-scale tests at Lehigh, for example, to study the behavior of those critical details at reasonable scale. And then the shaking table test here at UCSD, which is a very large structure, which is not as large as the real structures are, but captures the essential performance issues at the scale they're acting at. And so what the various groups are doing, for example, Arizona does numerical simulations which kind of show us how the overall structure would behave, how the real system will actually perform. At Lehigh, we're working on better details and connection details tested at large scale, so we get the right behavior because we're testing at a large enough scale. And UCSD is really showing us how the overall system would perform in an actual physical test.
That test will take place at one of the most unique facilities in North America.
Behind us, we have what we call the NEES UCSD shake table. NEES stands for Network of Earthquake Engineering Simulation, and is located at UC San Diego. This is the largest shaking table in the United States, and as you can see, it's an outdoor environment. Being outdoor has the advantage that we don't have the space limitations in many other shaking tables that we see in the United States or abroad.
NEES is it's an operating company, the actual organization that stands for the Network for Earthquake Engineering Simulation. We are funded by the National Science Foundation. We operate 15 different equipment sites around the country, which are all linked by information technology capabilities. The goal being that we test large-scale structures, geotechnical specimens, and tsunami specimens in one of our sites to examine earthquake performance of these systems. This is a new approach to research in that it's collaborative, it's shared use facilities, so I can go in and use the equipment at the University of Minnesota as if it's equipment in my own laboratory. So we eliminate a lot of the resource problems that typical universities have where they don't have the right equipment to run the tests that they need. It allows researchers around the country, principally university faculty, to do more involved, more complicated, more realistic kinds of testing so that the country can benefit from improved knowledge about how different systems, buildings, bridges, dams, different kinds of systems perform under an earthquake or other kind of extreme loading.
This shake table has been designed for different scenarios. The table can hold 2,000 tons. So if we put it in terms of how many cars or so, it will be of the order of 1,000 cars piled one on top of the other, 1,000 trucks. That's the biggest size. That's the structure we have at the back here. Weighs of the order of 400 tons, so we can still place 5 times more weight than expected. Why do we do this? Maybe that we don't test a building structure that is somewhat light, but we may want to test soil structures. Let's say we want to take very large soil containment structures like retaining walls. They are very heavy, and the table is geared for this case.
To move things of such massive scale requires some unique equipment.
We have some gigantic, very high performance actuators. These actuators can drive the table at about 6 feet per second, or 1.8 meters per second. They have a combined force capacity of 700 tons. And they have a stroke of plus or minus 26 inches. In terms of power, may be equivalent to what is spent in one night by a neighborhood between 5,000 to 10,000 people in one night, and we spend that in 45 minutes. Now, we cannot draw all that power directly from the grid because we create a huge problem, and we can do is we just take a little bit at a time and store it as potential energy. We just, like if we are inflating a balloon very slowly, and we we inflate the balloon and then we let go, and the energy goes into the actuators.
The balloon that Jose refers to is actually a huge array of pressure accumulators. You can think of them as giant compressed air tanks, except in this case, oil is pressurized in the tanks. That pressure is stored energy, the energy that will drive the table's actuators. The accumulators are connected to the actuators through a serpentine maze of high-pressure feed and return piping. The actuators that move the table are essentially giant piston jacks, very special jacks that can be precisely controlled. With one actuator at each end of the table, they push in unison to recreate the ground motions of a seismic event. During a test, all the weight on the table, up to 2,000 tons, actually floats on a thin film of high-pressure oil in the hydrostatic bearings that support the table. These unique facilities of the UCSD NEES shake table allow researchers to simulate large-scale seismic events with more control and accuracy than ever before, a capability that serves the needs of modern engineering.
The code requirements for seismic design are much more pervasive. Really across the majority of the United States, there have to be considerations of seismicity. Even in Texas, where I come from, that's a requirement. So that has forced us to develop answers for engineers on how to design structures and seismicity in areas they wouldn't even considered it before. Then also with the advancement of the industry, there's more needs required, more applications required, more interest required, so we have to satisfy this expanding need. And what we're testing here is the performance of these floors and roofs, actually how they perform in a seismic event. Little is known about this performance, so this program is one that both analytically and test out at the site here will determine code ways that you can now design properly the floor and roof to withstand seismic loads.
Those floors and roofs, or diaphragms, are made of a ubiquitous concrete material, pre-stressed, precast concrete. Dave Dieter, president of Mid-State Precast that is providing many elements for the DSDM test structure, explains.
Pre-stressed precast concrete is a process of producing concrete members in a controlled manufactured environment. Pre-stressed concrete in particular is a process of using concrete which performs well in compression and high tensile strength strand which works very well in tension, and combining those to produce a product that is very cost effective and very high strength. In essence, when we are pre-stressing elements, we are putting tension into the strand prior to placement of concrete. Once the concrete has cured, it clamps or binds the strand, which induces forces into the concrete, which makes it a higher tensile strength. That then allows, under normal loading, for the combination of concrete and stressing to perform well. The advantage of precast concrete are durability, fire resistance, and corrosion resistance. And that's what an engineer really looks at when they're designing a project. From an owner and architect's perspective, they'll be looking at the shape, texture, and what the finishes look like. And precast concrete can deliver those expectations and needs for the architect. From a contractor's perspective, scheduling is critical and important. Precast concrete outperforms conventional construction due to the inherent nature of pre-planning and pre-production of the product, so we can shave months off of a schedule, which really impacts the total cost of the project. A project that you may not know is precast and pre-stress is the MGM Grand in Las Vegas. A 5,000 room hotel with 15,000 pieces of precast at one time was the world's largest hotel. Was constructed in 9 months, and that I used the precast, pre-stress technology. Mid-State Precast started in the late 90s building the Paramount structure on 3rd and Mission in San Francisco. It is currently the largest precast structure in the state of California. Other examples of precast projects that Mid-States has been involved with is the construction of the UC Galen's Arena, the Ontario Community Event Center, Fresno State Save Mart Center, parking structures, office buildings, and schools. In this project, there are over 100 pieces of precast and pre-stressed components. And of those components, Mid-States Precast is producing the columns, beams, spandrels, double T's, and shear walls.
The key element supplied by Mid-State that is a focus of the test is a component called double T's.
The double T is a horizontal member that is used as a diaphragm or the floor that is built in a systematic process of stripping, pulling the pre-stressed strand, placing concrete, finish, and curing.
Another floor element, or diaphragm, is made from a unique concrete material called hollow core.
Hollow core plank is called hollow core plank because there are a series of hollow voids through the plank. These hollow voids make the plank 30 to 40% lighter than if it was regular concrete. Hence, a normal 8-inch cast-in-place concrete slab would weigh about 100 pounds per square foot. This product weighs 65 pounds per square foot. It reduces the load on the structure, which in a seismic occurrence is very helpful because the less weight that the shear resisting elements have to resist, the better off your structure will be, the easier it will be to handle earthquakes. This Irwindale facility has probably produced over 60 million square feet in the last 30 years, and it's used on a variety of structures that we have all been in. We use an awful lot of in wineries, and we build a lot of caves underground because it can support very, very heavy loads. It's only limited by imagination. What do you want to use it for? The concrete that is used in the manufacture of hollow core plank is zero slump, or the consistency of wet beach sand. That's to make the hollow voids, which are constructed much like a child putting his hand into a bucket of sand at the beach that is wet and being able to form something and pull his hand out, and it causes a hollow void. This particular type of plank utilizes a very long casting bed, in this case 750 feet long, 6 different beds. The product has 3 different mixes that go into the manufacture of the mix. The first mix covers the strand basically. They also put water on the strands at that particular point to get a little better paste for the bonding of the strand to the concrete. Immediately after it passes through that process, we come to the middle part of the mix where concrete falls down and is driven, compacted, and driven through mandrels that are moving back and forth on the machine. This compacts the concrete and moves the concrete around these mandrels, creating the hollow effect on the plank. Following that, In the third process, this is all happening in the length of the machine, which is probably only 15 feet in length. A very thin top layer is applied to screed off the top. The process occurs very much like extruding a piece of bologna, except our bologna's got a series of holes in the middle of it. The product is extruded at roughly 6 feet a minute. And it's one long extrusion, 750 feet, and when the concrete has achieved sufficient strength so that the steel adheres to the concrete, we go in and we cut the panels to the desired job requirements, where we inventory it in the plant. So when the project that they are made for is ready to go, they're put on trucks and carried to the job site and installed by construction crews.
The job site for these hollow core and double T planks is the NEES UCSD shake table, where they are some of the many components comprising the unique DSDM test structure. Despite using the largest shake table in North America, the researchers had to devise a special solution to accommodate the massive structure.
For this test, we wanted to have a very long floor span. This is the largest shake table in the United States, and because we wanted to test a floor which had to be wide or long sideways, we actually had to spill out over the shake table. And so these large beams behind me are what are called outriggers that Jose Restrepo designed so that our structure could actually be wider than the table but still move with the table.
This is a portion of a hotel building or a portion of a parking garage that is very oblong. And we're testing these diaphragms, these flexible diaphragms. So this is only a portion. We build this portion at 1/2 scale. Why do we do that? Because we cannot build it at full scale. It will be twice as wide, twice as tall, twice as heavy, and we just cannot cope with twice as wide. And nobody can indeed cope with twice as wide for this weight. There is no facility in the world that can do this. So we decided to build it at 1/2 scale. How big is the real structure from this? It can be in plant. It can be 1 to 2 times a football field. When we look at it, and it's half scale, already it's 3 times as wide as the shake table itself. So what do we do with a structure that is 3 times as wide as the shake table? What we have done is place some outrigger beams, and then they are mounted on some very fine hydrostatic bearings. The building is actually sitting on or hydroplaning on grease and oil combined. So the structure is skating above that, and then we can transfer this movement as if the structure was completely attached to the shake table platform or it had been placed on a foundation somewhere in the country.
Under the supervision of Jose Restrepo, this man, PhD candidate Matt Schottler, commanded all aspects of the test, from construction and instrumentation to planning the test sequences. Once the special foundation was in place, the precast elements were assembled. Matt describes the process.
After the foundation beams were placed, the columns and walls were brought in. The columns are gravity load columns designed to carry the gravity load, but not designed to resist the lateral forces of the earthquake. The walls are designed to carry the loads that develop during the earthquake as the floors move horizontally due to the ground moving. They're a post-tensioning rocking wall, which means that the walls have a post-tensioning strand. The post-tensioning strands act like rubber bands clamping the walls down to the foundation. Those post-tensioning strands provide the clamping force that pulls those walls back into place, providing a self-centering mechanism that brings the structure back to its original position after the earthquake. After the walls and columns were in place, the beams connecting the columns on the first 2 floors were put into place. We have 2 different types of beams. We want to see how the 2 different types of beams perform during the earthquake. So with the beams in place, it allows us to crane in the floor pieces. The floor pieces on the first floor are the topped double T's. A metal reinforcing mesh is laid on top, which is then embedded inside of a concrete topping. So after the topped double T system, on the second floor is a topped hollow core system. After the first 2 levels had their concrete topping placed over them, we moved on to the third floor, which is a pre-topped system, meaning that the concrete topping is already embedded in those elements. On the pre-topped system, since there's no concrete cover to place over the double T's, the connection between double T's is made with a welded connection. The ends of the floors are connected to the walls with embedded plates in the floor system and embedded plates in the walls. A welded connection is made between the wall and the floor. So in total, the system is this. The forces that develop in the floor travel through the floor to the walls, down the walls, and into the foundation.
The structure is completed and resembles many a building we may commonly experience. But the similarity ends there. Instrumented with over 600 sensors, the structure is designed to serve a very special purpose.
The shake table test is primarily a calibration tool used to validate or calibrate the computer models that have been developed in which we are trying to estimate the seismic forces that developed during the earthquake.
We have these models built and we've performed computer simulations of the structure. What we don't really have yet is verification that the way we're modeling the system is accurate. And there's all sorts of different effects that you might have due to boundary conditions or the way different parts interact that you can't really say, you can't really specify with a level of certainty until you see it with your own eyes. From looking at the 600 different channels and instruments, we can compare 600 different things on our model, from the overall behavior to the local behavior, and figure out why our model is acting differently.
The 640 sensors are distributed over the 3 floors and also at the foundation level. We have various types of sensors, including string potentiometers here, measuring relative deformation, as well as displacement transducers, ones here, which also measure relative deformations. To measure global deformations or displacements, we use GPS devices which are located on each of the 3 floors. Those will give us the displacement of each floor relative to a fixed point. We also have cameras that we're using to capture the crack patterns that develop during the earthquake. We also have accelerometers, which are very sensitive and can pick up the vibrations of the structure even due to the wind. We use the accelerometers to come up with an estimation as to the forces that develop. We're not able to directly measure the forces, but by the accelerations that we record, we can try to determine what forces were felt by the floors. Inside the concrete, we've embedded strain gauges on the reinforcing bars. Those will measure the stretching or the compression that occurs during the earthquake inside those bars. Those strain gauges tell us how much a bar needs to stretch or compress during an earthquake. Each sensor has its own wire. Each wire runs from the sensor down underneath the shake table to a data acquisition node, which then sends it to a computer that records the information. Since we know where each sensor is located and we've identified it with a unique tag, we could then go back and look at a series of sensors, how they performed, what results they gave us. We could look at individual sensors or compare one sensor to another.
What we're going to take from this test is we're going to look at how the different parts interacted, and if we have parts of our model that didn't behave properly, we're going to identify what about our model was different about what happened here in real life, and we can make the modifications.
With the sensors deployed and checked, it is time to start the series of tests. The first step is to raise the structure, allowing the outrigger beams to ride on the hydrostatic bearings as the structure is moved on the shake table. The lifting is monitored closely by a cadre of technicians in the shake table's control room. From here, all the table's actions are precisely controlled by computers that will set in motion all of the seismic tests.
We're ready to load the inner pack jacks.
The building is lifted ever so slightly,
2480, 2490.
only a couple of millimeters at a time, until it rides on a thin film of pressurized oil.
Stable.
Finally, it is time to exercise the table. The first motion is slow and deliberate, calculated to make sure all systems are functioning properly. With eerie moans and uncommon noises, the actuators slowly move the table back and forth. And just like that, an entire building moves, gliding gracefully, precisely, and under the control of the researchers. The shakedown is successful. The table is functioning properly, and sensors are providing data as expected. Soon, it will be time to test. While Matt Schottler spearheaded activities at the Shake Table facility in preparation for testing, another PhD candidate, Dichuan Zhang, has worked for years with Robert Fleischman at refining the models that direct the design methodology of the test structure. The kind of computational models that the DSDM project is designed to refine and perfect so they may be used to improve the future of design.
This is a model of the shaking table's test structure. This is showing the model simulation for the Berkeley MCE earthquake. And the red and the blue is showing the axial stress. The red means the axial stress is tension open, and the blue one is showing a compression of panel close.
Another of Dichuan's models is a full-scale simulation of a 3-story building about as big as a football field that will be used to calibrate structural factors for future design.
So this 3-bay parking garage structure, we have a ramp modeled in the middle. So it's like kind of real structure. We have the 4 side shear wall and the 2 longitudinal shear wall. We will use this model to calibrate the design factors like that. But first we need to verify the model is accurate. Use the Lehigh test and the shaking table test.
While testing the structure will calibrate and verify models such as Dichuan's, it will also serve another purpose. Robert Fleischman gives us an overall view of just what is being tested and why.
This test, as Jose Restrepo has said many times, serves 2 purposes. It's a demonstration project. We can demonstrate that the design works for a given earthquake, but it's also a way of calibrating or verifying our models. And what we're testing in the structure is actually 3 different floor systems. That makes it a little bit unique. On the bottom floor, we have double T's that have a very thin topping slab on top with wire mesh. That's a cast-in-place topping slab. On the second floor, we have hollow core with the same cast-in-place topping slab. And on the third floor, we have just precast units, what we call a untopped or pre-topped system. There are cases where, for utilitarian reasons, you're going to need to put a thin topping on a floor to get a smooth surface. But there are cases where the floor system could be just precast units. And this is the concept of what we call a total precast system, a total precast solution where the entire structure is made out of precast elements. By going with a thinner slab, there's advantages in that you're lowering the gravity load on the system, the dead weight of the structure. You're also lowering the mass, so you'll be lowering the forces in the structure as well. And there's economics in having less concrete and not having to place the rebar. And so none of these systems right now are specified for an area like California. In California, the precast units currently just sit and you pour a very thick concrete deck on top of it and put rebar in it. So really, I mean, what the design profession is doing right now is saying there hasn't been a project like this to show us how precast could be used. So each one of these systems, if we are able to demonstrate their good performance, will represent an advancement in their geographical area where they could be used. So replacing a thick slab to a thin slab, or actually going with no slab at all, would represent more economical solutions, and we've got to prove that these things will be reliable. And so if we're able to specify a precast diaphragm that works in an untopped fashion, the ability to use a total precast solution in a high seismic area will be a reality.
Key to precast are the connections that tie the elements together. Robert demonstrates with one of the connectors being tested.
This is a proprietary connection, the JVI Vector. This is actually a half-scale exact replica that they've built for us themselves for this testing program. So if you can imagine in a real structure, everything would be twice as big. This piece would sit in the precast formwork and then would be cast into the concrete. And it has legs that allow it to anchor to the concrete, and it would be connected with a slug or some sort of bar to the another one sitting in the next piece, and they will connect the pieces. And this connection actually has pretty good shearing resistance, but it allows for a little bit of compliance that it gives when it's pulled, so that in cases of changes in temperature, the panels can breathe without cracking. And in the earthquake, it actually helps hold the structure together. So this is one of the things, one of the reinforcing details that we've used in the structure.
It is time to start testing. As project partners from across the nation gather, the structure is prepped. Throughout the shake test phase, the seismic records will increase in severity, culminating in an event that might occur once in 2,500 years. The first test, though not as severe, might be as rare, as it is simulating the kind of ground motion that might occur in Knoxville, Tennessee, something that, though volunteers might never experience, they must be prepared for. Before every test, the structure is subjected to smaller motions called white noise.
3, 2, 1, running.
These small motions establish a baseline of how the structure is responding, so final test data can be accurately calibrated and understood. Then, it is time for the first ground motion.
5, 4, 3, 2, 1, running.
The test is a success and the structure performs as expected. Next up is the Seattle Design Basis earthquake, a severe event that might happen once every 475 years. Matt explains what is meant by a design basis test.
At the design level event, it's an extreme earthquake. The design of the building would be such that you can walk away from the building, but the building may not be reusable. But as long as you're able to evacuate safely, the structure has performed as intended.
PCI 3, 270%. 5, 4, 3, 2, 1, running.
A visual comparison of the first two tests makes it clear that the seismic hazards faced by Seattle are more severe than those in Knoxville. After these two design-based tests, damage was as expected. Matt Schottler gives an assessment as well as a preview of what is to come.
So right now we're halfway through the test sequence. We've completed the design earthquake for the Knoxville site, and we've completed the Seattle design basis earthquake. So after the first test, which was the Knoxville design basis earthquake, there was really no damage to the structure at all. We had some minor crack propagation, so there really wasn't any damage after the first earthquake. After the second earthquake, which was the Seattle design basis earthquake, we did see residual cracking in the second floor, which was the topped hollow core floor, which is the floor we're on now. There is a joint between precast units. There's one precast unit underneath the topping here and one on the other side. Because the walls are located out at the ends of the floor, we do expect there to be cracks developing in the center before we would see cracks at the ends of the floor. And that's what we're seeing here with this crack running down the center of the floor. The third floor is the pre-topped system, the pre-topped double T system. The connection between precast elements on that floor is a welded connection. There has been just minor damage along the center joint between those elements as the concrete cracks. And after a design basis earthquake, it is quite likely there could be some minor repair work to do, which is what we're facing now. The repair work will be completed, and we'll continue testing for the Berkeley site. In the ensuing tests for Berkeley, we have selected 2 other ground motions that represent the hazard that faces Berkeley, California. And those would be an earthquake that occurs at a very close distance to the site, mainly a near fault or a near field ground motion. And those will be tested first at the design level and then at the maximum considered earthquake that we would expect for Berkeley. To give a comparison, the peak ground acceleration is about 4 or 5 times larger for the maximum considered earthquake in Berkeley compared to the Knoxville record that we've already run.
Due to the severity of the upcoming ground motions, the researchers implement extra safety measures.
Because of the extreme nature of this ground motion, we've added some precautionary measures. We've added 2 restraint towers on either side of the structure. The towers are there just as a precaution to protect the equipment down below, in particular the actuators underneath the table, and they're not touching the structure. They're actually set back 6.5 inches. We don't expect failure, but as a precautionary measure to protect the equipment here on the site, we've implemented safety measures.
Once again, it is time to test. As a further precaution, the team has decided to conduct the less severe Seattle test again to make sure the new safety measures are working properly.
PCI 3, 270%. 5, 4, 3, 2, 1, running.
While the purpose of these large-scale tests is to gather data with which to refine models and design methods, the raw spectacle of a test is undeniable. It's as if one is the lucky observer of a rare but staged natural phenomenon. The air is filled with the pitched strains of high-pressure pumps. Anticipation mounts as the countdown proceeds.
Running.
A deep moan emanates from the ground. And then, just out of arm's reach, an entire building moves, violently shaken. An earthquake occurs before one's eyes. As rock solid as concrete is, the structure lurches and flexes. Heavy thumping pounds the air. The ground resonates. Columns sway. Concrete spalls, small bits and pieces fall away. Concrete and metal clash and clang somewhere within the structure. And then, as quickly as it started, all becomes settled, as if the Vulcan power that shook the table retreats. The moans and groans diminish, and the table's small oscillations come to a slow, calm halt. The test is over. The structure survives the rigors and spectacle of the latest test, and the team is ready to move on. Robert Fleischman previews his hopes for the upcoming tests.
Next week we'll be testing the Berkeley motions, both a design basis earthquake and a maximum considered earthquake. And if the structure and the floors can survive through those, we'll have successfully demonstrated those systems for those demands.
Just prior to the day's testing, Jose Restrepo gives a preview of what to expect.
The structure is going to undergo 2 major input ground motions to earthquakes that simulate conditions in Berkeley. This is the highest seismic region of the country. And we are going to simulate this scenario with a record obtained during the 1989 Loma Prieta earthquake in San Francisco or nearby. And this has very high velocity pulsing. In fact, has 5 pulses, 1, 2, 3, 4, 5. So the structure is going to be very severely shaken. This represents what we see the conditions for a design basis earthquake in that part. What is a design basis earthquake? Is what we design for. We expect that at that point the structure will survive with some damage, yeah, but no significant. We are not going to see any loss of life. We may be able to see interruption to business operation, and we may have to patch here and there, but we are preventing at any cost the loss of life. A design basis earthquake has a recurrence interval or return period between 400 to 600 years. So that's more or less what we expect. So for the design basis earthquake, we use the Los Gatos record of the Loma Prieta earthquake right away, and that will be our design basis earthquake. We expect to see about plus or minus 6 inches of displacement under the Los Gatos motion for this structure, which means for the real prototype it will be moving twice as much, with plus or minus 12 inches. That's what you'll be moving, and the building may be moving relative to the ground more or less of the order of plus or minus 12 inches. We then move to a higher level, which is what we call the maximum considered earthquake. The maximum considered earthquake has a return period of about 2,500 years. So it's quite rare. For the maximum credible earthquake, which is that very rare event, we will use the same record, but we will amplify the accelerations or displacements by 1.5. So the structure is going to be subjected to 1.5 times more displacement demands than for the design basis earthquake. So we're talking about, for this test, of the order of plus or minus 9 inches. For the real building we will simulating, because this is a 1/2 scale model, it will be plus or minus 18 inches.
As the building is subjected to these displacements, Jose describes the forces and motions that will be generated in the structure and what the resulting damage may be.
As we shake, this building has 2 very stiff walls at the edges and is very oblong. So we shake the building and all the center part of the building will be flexing back and forth. And that's what we're testing here. That if we can test, because the inertia forces, the mass times the acceleration has to go through those stiff elements, we will have bending in that floor. That floor we call the diaphragm. And we are testing how to make sure that the diaphragm holds. That's why we are testing that oblong structure. Now, once we do that, the inertia forces go to the edges, and then they are picked up by these walls. And these walls are designed to rock. That they are different from conventional walls. These walls will uplift from the foundation. They are post-tension, so they are forced to close back, and they are designed for 0 to minimum damage, even at the maximum credible earthquake. In the design basis earthquake, we expect to see some yielding, so some of the connections may be stretching and dissipating energy as they go, but no severe damage. So it's something that we will observe, and we'll see some localized damage, but it's acceptable. So we accept that at design basis earthquake, we can have some localized damage here and there, and that's fine. So that's what we expect. For the maximum considered earthquake, we can expect severe damage. By severe damage, we expect to see several connections will be ripped off, will be damaged, maybe fracture of some reinforcing bars, but in the end the building will be standing, perhaps in a precarious mode. Perhaps in a real structure, we need to take that decision that building is no longer inhabitable and we need to demolish it, because we want to prevent the collapse that can translate into significant loss of life to the community. So we are going to probably, under the second shake today, so intense, we probably see a significant damage, but we don't want the building to collapse. And that's our objective for today. What happens in the actual experiment may be different, because that's the reason why we're doing research.
After years of work and preparations, the time has come for the penultimate of the large-scale tests. The tests are extreme, recreating events so severe they are unlikely to occur for generations to come. The researchers begin the test sequence with the Seattle design-based test to ensure the structure and all systems are ready for the rare and extreme occurrences to follow.
PCI 3, 270%. 5, 4, 3, 2, 1, running.
Success. We have to check everything close up, but it looked like it performed really well, so we're excited.
The team is ready to proceed into uncharted territory, the Berkeley design-based test, replicating forces experienced close to the Hayward Fault maybe once in 475 years.
PCI 6, 100%. 5, 4, 3, 2, 1, running.
At this level of accelerations and displacements, the actions of the post-tensioned walls finally become clearly apparent. As the ground displaces, the floors move laterally, and that force is exerted on the walls, trying to rotate them off their bases. But the flexible connections in the walls allow them to lift, and they are then pulled back down and repositioned by the tensioned strands within. It is time for the most extreme test ever conducted on such a massive concrete structure. The Berkeley Maximum Considered Earthquake. One we have little chance of experiencing, or so we hope.
PCI 100%. 5, 4, 3, 2, 1, running.
Once again, the test is a phenomenal experience. Swiftly, tons of concrete is rocked. The table and structure seem to fight each other as the towering mass is accelerated first one way, then the other. The walls lift and rock, pummeling the foundation. Strange pounding, bashing, pops and rattles fill the air. The top floor whips back and forth. From top to bottom, the entire structure sways ominously. The accelerating mass of the floors pushes the walls perilously close to the brink. In the end, all settles and the structure stands. The test phase is complete. With the task of transforming the results into practice ahead, Matt Schottler and Robert Fleischman comment on how the structure's performance and the test's successes will make that possible.
The structure went through 16 significant earthquakes, and those 16 significant earthquakes, we started from a low level, a Knoxville design basis earthquake, and at the end of testing, we were finishing with a Berkeley Maximum Considered Earthquake. As a whole, the test structure performed very well, especially in terms of performing its role as a calibration tool for our computer models. But the fact that the connections held up during the test and held up well during all of these tests means that the codification process becomes that much easier, because you've seen that it worked within a whole system, within a building system. So in total, the test structure performed its role in validating the computer models.
The testing program at UCSD has successfully demonstrated that our models that we built based on the Lehigh tests have a high level of accuracy. We're really excited about that because what this allows us to do is have confidence in moving forward with parametric studies. We look at all different types of structures all over the country, different configurations, different designs on the computer, and we can say that we have confidence in it because we predicted this test and we ran the test, and the prediction and the response are right on top of each other. I'm also quite hopeful that with the strong team that we have, we can actually truly transform our research into practice and get this into the codes. And so we're hopeful that the result of our work will save lives, will make the construction industry more competitive, will open up markets for precast concrete.
It has been many years and thousands of man-hours of the best minds and resources in industry and academia working together to improve technology, practice, and to make safer structures by building it better.